Hey everyone, welcome back. This is part 2 of our barbecue hacking series. In our previous episode, we set up a virtual machine and were able to obtain the Bluetooth traffic between that and our Android VM and the barbecue device. In this episode, we'll be looking at how to analyze that packet capture as well as how to connect up with the device to begin to start reading those temperatures.
Today's initial steps that we're going to be taking are going to be setting up a connection with the actual device. We'll then complete the pairing process with the device, and then we will enable notifications of the temperature data from the device.
Before we dig in too deep, I think it's useful to have kind of a high-level picture of what we're going to be working with here. And so I'd like to start with a little bit of background and information on how the Bluetooth low energy stack actually works. And so we won't need to be concerned with all the components of the stack, but it will be useful to kind of know how the higher level layers function so that we know what we're interfacing with. And so let's start by taking a look at the stack itself.
So initially, to get connected with our device, we need to know that the device is out there. So there's a process of discovery and advertising that's taking place. And this is handled through what's known as the GAP, or the generic access profile. So each device operates in one of two different ways. And so normally, you can have two devices operating as broadcasting, where there's a broadcaster and an observer, or the devices can be operating in a connecting mechanism in which there's a peripheral and a central device that connect together. So in ours, we'll see that they actually do use this connecting mode here, to where the peripheral, the barbecue thermometer, sends out advertisements indicating that it's available to connect to, and then our central device, or in this case our desktop, will send out that connection request. So once we get connected to the device, we'll then begin to interface with what's known as the GATT. Not that kind of GATT, this kind of a GATT. This GATT is essentially a nested structure that allows for different data points to be accessed from the device. In this case, the way that it's normally laid out is the GATT server is what's going to be running on the device that we're connecting to. So in this case, our barbecue thermometer is going to be running the GATT server, and the GATT client will be initiated from our end with our program when we connect to the device. In the previous slide, we kind of discussed, just at a high level, we have what are known as services, we have characteristics, and then even below characteristics, we have something known as a descriptor. Let's take a look at what this looks like for the device. And so we can see that there are actually 4 services running on our device. The first 3 of these are kind of just default. They use some of these default fields that are defined in the Bluetooth standard, such as device name. We have things like the model number that's running in here. We have a firmware revision. We've got manufacturer name. Now, the information that we're really going to be interested in is going to be for this 4th service that's running here, and it's just kind of an unnamed service. This is a custom user developer defined service that's running, and we can see that there are a total of 5 different characteristics that are available for that particular service. In this case, the developer has actually provided some descriptors for each of the different characteristics that are running here. And so you may have noticed that it shows characteristic user description. These sub handles that you see here for this particular characteristic are what are known as those descriptors. And in this user description, they've actually just encoded some ASCII text that provides a description of what data is actually being stored for this characteristic. And I've gone ahead and just made it to where it's easier to see this. So for the first one here, the text actually reads setting result. This one reads real-time data. That sounds interesting. The handle that we're going to be interested in here for our device is going to be this hex 30 handle, because it says that's where the real-time data is likely stored at. And remember that for whenever we start looking at our packet capture. Now we're going to take a look at our actual packet capture file here. To do this, we're going to need to use the Wireshark tools. If you don't already have Wireshark installed, it's fairly easy to get installed. You're just going to simply type in sudo apt-get install Wireshark. I've already installed this, so it's going to tell me it's already installed. After you run that, you should get a copy of Wireshark. Once it's opened up, we're going to go ahead and open up that packet capture file that we copied over to our desktop in the previous step. So we'll just click and open that up. I've gone ahead and just scrolled down a little bit in my file here. Your output might be a little bit different than what I am showing on my end. That's just based on the different Bluetooth devices that I have in my household when I was running this. One thing you may notice as you first start to scroll through this is you see these received LE Meta, LE advertising report. And in the previous section, section, we kind of talked a little bit about the GAP and how devices can operate in a peripheral or a central device mode, and the way in which they kind of advertise that they're available to be connected to. All of these LE advertising reports are different Bluetooth LE devices that are in the house here that are sending their beacon out saying, hey, I'm available. Here's kind of my basic information, such as my MAC address if you want to connect to me. Once the actual connection process starts, you'll start to see commands being sent across, and pretty much what happens is our central device, when it begins to initiate a connection with it, wants to get some information about what kind of services and features the actual peripheral it is connecting to supports. So it goes out and finds things like, what version of Bluetooth does it support? What version of security and encryption and things like that does it support? So it sends several of these commands to get that information. After it gets that information, then it pretty much wants to read in the GATT table so that it knows what's available. These commands that you start to see here, we see that it starts to read in the different services that are available. It then moves on from the services into enumerating the different characteristics. And then after it finds the characteristics, it moves into kind of identifying the different descriptors that might exist on those characteristics. So the main commands used to communicate with the GATT server can kind of really be narrowed down to just a few different commands. The first one being read, where we're able to read the value that's stored at a particular characteristic. We could read the value stored here at the 3 handle, or maybe read the value that's stored here at the 30 handle here. We can also do things such as writing values to handles. You can write an actual value to a particular handle, such as 29 here. We can also do other things known as notifications or indications. Basically, notifications allow the device itself to pretty much send that's stored at a particular handle. As every time it changes, it will send it to the central device without us having to go to the device and send a read request. So to make it a little easier to start to analyze the traffic that's taking place between our device, we're going to look a little bit into how to use filters inside of Wireshark. And so for the particular protocol that we're using here, we kind of discussed how there was these basic commands that can be performed using the attribute protocol. As we see here, we have some of these different protocols being listed out, and the attribute ones are going to be the ones that we're most interested in. To apply a filter in Wireshark, we can simply type in BT, and then we can type in ATT. So this just says using Bluetooth attribute, I want to filter, and then I essentially want to be filtering on what are these opcodes. There's a few that we're the most interested in. Those are going to be the read ones, the writing ones, as well as the notifications. So I'll just type in .opcode, and then I'm going to set it equal to, and I will choose hex A. So what this is this is going to filter and show us all the traffic using the attribute protocol that is essentially sending a read request. Here we can see that we only actually have one single packet that's getting sent asking for a read request, and it's performing a read request on this handle of 18. If we look at our chart here, we can see that handle 18 is a mapping to the firmware revision string. And if we then want to look at that, we can see kind of some additional packet information that's digested here by Wireshark. That firmware string here is running on the device information service, which has this hex 180A value. If we look again at our chart, we can also see that does line up with what we have here, to where we can see we have a device information service that's running with this hex 180A. In addition to sending a read request, the related action for that is going to be reading the response for that. To filter and see that traffic, we can type in this hex code B, and that will just show us only the read responses that have come in. And since there really was only one actual read request, we can see that there's only one read response here. We can see that it came from the 18 handle here, which was that firmware revision string. At the end, this is the actual data that it returned. And so that's the actual value that's being stored on that GATT server for that particular handle. Before, we were kind of looking at these filters individually, but maybe we want to kind of see it all in one view here. You can actually use some of these Boolean operators such as and or with your filters. The one I'm going to be using here is called the or operator. You just type in the double pipe symbol here, and then we will type in btatt.opcode, and the other one that we wanted to see again was the response data, and we saw that that was filtered with the B code. Now we can kind of just see the request and the response all in one kind of filtered view here. We took a look at the read request, and so now let's take a look at what happens in terms of writes are taking place here. We can filter for our writes, the request, and the response using the hex 12. That will give you all of the attribute write requests that take place, and then we can also use the hex 13 here, which will show us all of the write responses that are coming through. And you can also see that we do have source and destination, so that makes it a little easier to know which device is sending what here. So we can see our VMware, which is going to be that virtual machine that we had running, and then we have our iBarbecue, which is going to be the actual thermometer device. The next command that gets sent here is sent to the handle 29. If we look here at handle 29, we can see that that is described by the developer here as account and verify. A value gets written to there, and after you write that value to that particular handle, we become paired and authenticated with the device. I've decided to just exclude that value just out of caution. I didn't want to run into any issues. You can probably find it online, or if you're following along, you should see what this value is. We're going to need it actually whenever we connect up using our Python program to this device. Right now, again, we're looking at this in a filtered view, so I'm going to add one more that pretty much enables showing the handle value notifications that are coming through here. There's a few other writes that take place, but the one that we're actually concerned with is going to be this write to the 34 handle. We can see that a write request gets sent to that, and the value passed to that is this 0B01 value, followed by about 8 zeros. After we send that command to the 34 there, we can see that we then begin to see these value notifications that come in from that 30 here and actually have the temperature data. We're going to need to know what the device's MAC address is. We're going to be actually using the MAC address for the Bluetooth device to connect with our barbecue thermometer. You can get that by pretty much going to any of these different packets that we see here, and you'll see we have a source and a destination. Mine is using a Texas Instruments device in here, and this is the MAC address here. It's going to be this code. So you want to write that down or note that down. You should also be able to just copy that out. If you do a copy on the value, that should just copy out directly the MAC address itself. Now that we've kind of run through that, let's actually play around with interacting with the device itself in real time. To do this, we're going to be using what's known as the Blues application. You'll need this installed. This is just pretty much the Bluetooth stack tools for Linux, and so to check and see if you have this installed, you can just simply run this dpackage-s blues command, and you should get back a bunch of information like this. If it does come back and tells you that you do not have that installed, install it by running essentially the sudo apt-get install blues command. Let's go ahead and actually test this out in real time. We're going to be using the GATT tool for this, which comes built into that Blues Bluetooth stack software that we installed here. So we'll just go ahead and run that by typing GATT tool, and then we're going to do -I, and this is going to put us into interactive mode. Once we get into here, we can go ahead and type this help command. This is just going to show us all of the different commands that we can potentially run with this tool. The first command that we want to run here is we want to connect with the device. We're just going to simply type connect, and then we're going to put in that MAC address of the iBarbecue device. Make sure that you do put in your MAC address that you pulled from the Bluetooth packet log there, and we'll go ahead and start connecting with it. And what we should see is that here shortly we should get a connection successful, and we should start to see that the connectivity light starts to blink on the device. So with that, we are now ready to write to that account and verify handle, and we're going to be using the character write request. And the way that this works is that this is going to send a command it's going to send a write request to handle 29, and then we passed in that connection value, and we should get back that it was written successfully. And as you can see on the device now, we have a solid connectivity. So we're actually now officially connected with the device. And the next step is that, if you remember, we want to then enable notifications of the temperature data. And the register, or the characteristic that we want to write to for that, is going to be hex 34. And so we're going to be writing the value that we saw in the capture to that to enable notifications, which happens to be this 0B01 and then 8 zeros. Once we write that, give it a moment, we should then start to see these notifications coming through. If we wanted to see potentially, how this works, I can actually start to touch the probe here, and as you can see, the values start to change on the temperature probe, but that we also see that there's values that are changing in there. So we can see that potentially those first 4 hex digits may correspond to the temperature here. Now, I only have a single probe plugged into this device right now, so we can kind of explore this a little bit more. What happens maybe when I move that probe to a different connection hole on the device. So I'm going to unplug it, and after I unplug it, let's see what happens. And then plug it back in. Now I've plugged it into the second port on here, and we can see now that all these other ones have this default F6FF value, but now that it's plugged into port 2, we can see that the data is changing for that one. Whenever I come out here and touch the probe, we can see that these values start to change for those for that. And so the way that this is designed is each of these hex values for 4 digits corresponds to the temperature of that particular probe. And this device has 4 probes, so we can see that each one of these will correspond to the temperature when all 4 of them are plugged in. Now that we actually have the temperature data coming through here in real time, it makes sense to try to figure out how the actual temperature data is stored on the device here, and what the format is for actually getting it from this hex format of data into our friendly 79 degrees in Fahrenheit data. So right now we can see that 79 degrees is showing up for this device, and I currently have it plugged into the second spot here. So that means that we're going to be concerned with how does 0401 convert to 79 degrees Fahrenheit for this device. To do that, we can kind of build out a table, if you will, of these values. So if we know now that 0401 is equal to 79 degrees, maybe let's go ahead and also see if we can get a few other values that we can use as reference, so that it'll be easier when we start to take some guesses at how this data is stored. We'll have some other values to work with. So I'm just going to touch the probe again here and wait until it changes values. And so an 88's coming through as 3601. Okay, so now we know that 88 degrees, this displays it as 3601. So I'm going to add that as another value. We saw that the value 0401 somehow should map to 79 degrees Fahrenheit, as well as that this value 3601 should map to 88 degrees Fahrenheit. So let's see if we can figure out how this encoding is working here. So I've just opened up a calculator here on my Ubuntu, and I've put it into programming mode, and then I've chose hexadecimal for my input. And so let's see what happens if we type in 0401, and over here you'll see it automatically will tell us what this number would be in base 10, which is just our decimal numbering system. So converting this value into decimal numbering system, we get back 1025. That seems like a really large number, and doesn't really seem to match this Fahrenheit number at all. Maybe if I swap the order of these and do 0104, we now get kind of this lower number, which is good, but it still doesn't quite equal 79 here. And so had to think about this a little bit and think how this device would be sending that information. And what we'll find is that in the US, Fahrenheit is the standard, but everywhere else, everyone is using Celsius degrees. So I wanted to see what these values are in Celsius, and maybe that would give us some insight into how this data is being stored. And so if we open up the browser and go to here, we can type in this just simple conversion of 79 degrees Fahrenheit equals about 26.11 degrees Celsius. So if I come back over to my text editor here, let's just note that this equals 26.11. And what about for 88? So if this was 88, we'll see that it should equal somewhere around 20 or 31.11. Okay, so with those values, these are what we should expect to see if it was somehow in Celsius. And you may have noticed that this 26 looks fairly close to what we saw here with this 260, but we had to reverse the digits to get it to come out to this 260. The way that works is that in a lot of hardware systems and things, there's something known as Indianness. And by Indianness, it means essentially the order in which the data is read. You have something known as Big Endian and Little Endian. And what this means is that where is the most significant value stored at? In Big Endian, this means that the big value for this is going to be on the left side, and then the smaller value is going to be on the right side. So in Big Endian, when we plugged this in, if we read this as a Big Endian value, so if we plug in 0401, this is pretty much assuming that we'll just read the value as it is as 0401. The big value is on the left, and then the smaller value comes on the right. So that is what Big Endian would be, and we see that we would get a number of 1025 in decimal if we convert from hex. Now, if it's Little Endian, we see that essentially we read the right value first and then the left value here to get our number. And so if we convert this to 0104, which is how the computer will interpret this in the calculator to say that this is the most significant and then 04, what we get is 260 here. Now 260 is very close to this 26.11 that we got up here. If we put in just 26, we'll see that we get 78.8 Fahrenheit. Now the sensitivity of this device is actually 1 degree, so really it's only operating and using 1 degree increments and decrements. Let's go ahead and see if this works also for our other temperature now. So we had 3601, and if we remember, Little Endian is the format that's being used for this, so that's going to actually, what we want to see the value of is 0136. And so we plug that into our calculator here, 0136, and what we get is 310. And if you remember, it looks like they just divide this by 10 to get the degrees in Celsius. And so 310, or 31, comes out to be 87.8. You round that up, and that does equal the 88 degree Fahrenheit reading that we saw coming through. Now we know how this data is being encoded for the temperature.
All right, and that wraps up today's session. We were able to take a look at how the Bluetooth Low Energy Protocol works. We dug in a little bit on the stack and how GATT servers work, and then we were able to use the Wireshark tool to apply some filtering rules, analyze that traffic capture that we did in the previous session, and ultimately learned how to read the temperature value data, getting into Big Endian, Little Endian, and those kinds of things. So in our next video, we'll start to build out our actual Python application, so stay tuned.